Hi, welcome to IM Group's series of webinars on new features of SQL Server 2014. My name is Stephen Leach. I'm a Principal Consultant with Information Management Group, and this webinar will be focusing on a new feature called delayed durability. Okay, so I will progress on to what we're going to cover in this half-hour session. So first of all, have a talk about what delayed durability actually is. The modes available for it, the syntax to make use of it. Then we'll discuss how transactions are actually made durable, which will make a little bit more sense when we get there. Have a think about what scenarios we might want to use delayed durability in, and then finally we'll wrap up with some tests and some results to see what performance improvements we can get through making use of this new feature. If you want to ask questions, there should be a feature available. I may be able to respond to them throughout. If not, we'll take a look at them at the end or respond to them offline. Okay, so let's kick off with what delayed durability actually is. So, normally, when a transaction is executed with SQL Server, upon commit, the transaction log records are written to disk before control is returned to the client. So this can cause some delay while we're waiting for I/O operations to complete. With delayed durability, rather than writing transaction log records directly to the disk, they're kept in a buffer and then only written to disk when the buffer is full or some specific conditions occur to cause the buffer to be flushed to disk. This means that there's less contention for log I/O and control will be returned to the client quicker. It does have some implications. It doesn't come for free, and the key point to be aware of, and this is a biggie, is that the D of ACID in ACID transactions is relaxed when using delayed durability. So before we move on, let's quickly review what ACID means in the context of transactions. So ACID is an acronym standing for atomicity, consistency, isolation, and durability. So atomicity meaning everything or nothing is written, as in the whole of the transaction is successful or nothing is successful. Consistency means we move from one valid database state to another. Isolation means these transactions happen in isolation of other transactions as if they were happening serially. So this is why we get locks taken out on records or tables. And then finally, durability, as in once the transaction is complete, it's complete for good and there's no chance of data loss, assuming you still have your transaction log. And what delayed durability does is it relaxes the D of ACID, meaning there's a risk that upon catastrophic failure, you could potentially lose some data that you thought had been written to your database. What it doesn't do is it doesn't affect the A, C, and I of ACID at all. So we still have all or nothing, we still get consistency from one valid state to another, and our transactions still happen in isolation. It's purely the durability. So the key thing to remember here is that making use of delayed durability, we potentially have the opportunity for data loss. Okay, so I have a very brief understanding of perhaps what delayed durability is. So in SQL Server, there's three modes available. So delayed durability is set at the database level, and by default it's disabled, as in all transactions are durable. So this is the functionality that you were used to with SQL Server 2012 and previous. As in once a transaction is committed, it's committed for good, and the data is there. The second option is delayed durability transactions are allowed, as in by default when the transaction executes it will still be fully durable. So if you made no changes, so if you change your database to allow delayed durability transactions but made no changes to your applications calling it, then nothing would change. However, making use of the new extension to the commit transaction using the keyword delayed durability on, we can target specific transactions to have delayed durability. Alternatively, with in-memory OLTP natively compiled procedures, we can use the begin atomic with delay durability equals on. Then finally, the third option is forced. And this means all transactions against a database will have delayed durability. So what this would allow us to do would be to, at the database level, set delayed durability to be forced, and then with no changes to our applications, take advantage of this new feature. Now, this is perhaps good and bad, depending on which side of the coin you want to look at. If we had a scenario where we wanted to use delayed durability but didn't have the time, resources available to re-engineer our application to take use of it, we could quite simply set delayed durability to be forced at the database level, and all transactions will then have this functionality. The other side of that coin is exactly the same thing. We set delayed durability to be forced at the database level, and there's a risk here now that all our transactions have delayed durability, quite easily set, but then we run the risk of having data loss. So it's something to consider if you are looking at using this feature. There's a quick win to set forced, but at the risk of unintended side effects that you're not necessarily aware of in your applications, or to have a more targeted approach and allow it, and then to target specific transactions within your application to make use of this feature. So by default everything is disabled, which is, I think we'd all agree, how it should be, so we don't have any nasty data loss creeping into our applications that we're not aware of. Okay, another point worth making here is that the transaction isolation level is unaffected by this in terms of read committed, read uncommitted, serializable. It's purely the durability portion of our transactions that has any effect. Okay, so now we know what our available modes are. Let's take a brief look at the syntax for using this. So just looking at setting a database level, it's simply an alter database statement. We're setting delayed durability to disabled, allowed, or forced. Similarly, if we are working with a database that has allowed delayed durability, when we commit our transaction, we can use commit transaction with delayed durability equals on. It's worth noting that the database settings override the actual statements. So for example, if we had a database with delayed durability set to disabled and we executed a commit transaction with delayed durability equals on, we would still have a fully durable transaction. So even if you have a perhaps slightly gung-ho developer who decided to commit his transactions with delayed durability equal on, as long as the database doesn't say allowed or forced, then they will have no effect, other than committing the transaction as normal. Okay, so the syntax for using it is quite simple, quite straightforward. There's nothing special really going on there. So, mentioned near the beginning that when a transaction has delayed durability, it is written to a buffer rather than directly to disk. However, at some point, we clearly need to go to write this to our transaction log. So this can occur in 3 different ways. The first occurrence is a fully durable transaction that alters the same database. So this scenario would only arise when we have our database level setting of delayed durability equals allowed. And what would happen is we execute a transaction with delayed durability, and then another process, or maybe the same process, comes along and executes a second transaction that is fully durable. And that causes the buffer to be flushed to disk. And that's necessary when we think about it, because we need our transactions to be consistent with each other. So if our second transaction came along that was fully durable and we didn't flush the buffer, then we would have the second transaction written to disk, potentially changing the same data that the first transaction had changed. And then if we lost our database, we would come back up, we would have an inconsistent state in the database. So, in summary, a fully durable transaction makes all previously delayed durable transactions fully durable. The second way we can ensure durability of our transactions is we execute the system store procedure SP flush log, and this flushes the transaction, the log to disk. The third way is, well, the log buffer is full and SQL Server needs to write it to disk anyway. Now the log buffer is 60 kilobytes in size, so as we execute delayed durability transactions, this will fill up, and when we reach the 60 kilobytes limit, it's written to disk. So we are delaying the writing to disk, however, not forever, only until our buffer is full or we have some application initiated or user initiated scenario happening. So a couple of points worth noting here. If we have a catastrophic failure or an unexpected shutdown and restart of SQL Server, we're going to lose the transactions that are in the log buffer that haven't yet been written to disk. Which is as we would expect. However, another scenario that seems slightly odd is that if we take a log backup, backup of our transaction log, that does not guarantee that the transactions in the buffer have been written to disk. So potentially, we would, even if we think we are backing up our transaction log, we're not necessarily doing so completely because we still have the data that's not been flushed to disk. So it's worth bearing in mind that if you are changing your databases to use delayed durability, you might want to revisit your backup and data recovery plans and perhaps flush the buffer to disk using SP flush log before taking a transaction log backup. Okay. So now take a quick look at what scenarios should we use delayed durability for. Clearly this is a new feature, but not necessarily suitable for all cases. You should only use delayed durability if you can tolerate some data loss. So that is, we have a failure of SQL Server, it restarts, it shuts down, we lose the server. We are going to lose the transactions that are in our buffer that haven't yet been written to disk. This is crucial. So if you have a system where every single transaction counts and you can't afford to lose any, then delayed durability probably isn't for you. So that's the downsides of using it. So if it's just going to give you data loss, why would you use it? Well, it's there to resolve bottlenecks on transaction log writes, or when you've got a particularly high contention rate. So if we have lots of transactions happening on our database, potentially we are waiting on transaction log writes to happen. Now we can delay those by using delayed durability, which would mean that we get potentially better throughput. Although it's worth noting we still have to write the transactions to disk at some point, particularly when our 60 kilobyte buffer fills up. But because we're doing one write there, it will overall be quicker. Rather than doing lots of small writes, we're doing one bigger write. So we will get bigger throughput. So that's when we should be using delayed durability. If we have a particular problem that we can't solve any other way and we can tolerate some data loss, it should never be more than 60 kilobytes. But you're not necessarily going to be sure which 60 kilobytes, if you have a particularly complicated application, then delayed durability might be something worth considering to resolve these potential performance problems. Okay, so we now know potentially why we might want to use it and what scenarios we would not want to use it in, as in can't tolerate data loss. So, saying that this hopefully will solve problems with wait on transaction log writes. So it seems prudent to do some tests and check to see how this works, see if it really does give us the results that we would like. So I've set up some tests that I've run on my laptop. Now, any results we get here will necessarily be different to anything other people might experience, different hardware, different workloads. If I explain the two scenarios I wanted to look at to see how this worked. I wanted to see what the performance was like between using delayed durability and using fully durable transactions as we're used to. And the two scenarios I wanted to look at was a workload that involves lots of small inserts or a workload that involves fewer large inserts. So to do this, I set up two databases, one that had delayed durability set to disabled, one that had delayed durability set to false. So I knew that my transactions were either going to be fully durable or delayed. The databases were set in full recovery mode. Those databases were growing to sufficient size, so there was no database growth going on while we were executing the tests. And so I ran one batch that involved lots of small inserts, inserting one row at a time for 200,000 rows. Then use the same data sets, but rather than inserting one row at a time, I inserted 25,000 rows at a time. So this gives us two different workloads, one where we are inserting, both where we're inserting the same amount of data, but one in lots of small inserts and one large inserts. And this is particularly relevant when we think about the size of the buffer. Okay, so having run these tests, the results are in. And you can see from this table here, if I just walk through it, because it's not totally clear exactly what's going on here. The first row is a fully durable database, so as we would normally have it, executing 200,000 inserts. And that took a duration of 92 seconds. The second row is when we were doing exactly the same inserts, but with delayed durability set to on, and there's a quite dramatic improvement in the duration here. And so duration isn't necessarily a measure of everything, because there might be other little bits and bobs going on. So we looked at the number of writes that happened there. We had 200,000 writes for our fully durable transactions, but only 4,500 writes for when we delayed the durability of our transactions. So what's happening here is we can see this, the log buffer being flushed every so often. The number of bytes written is a bit smaller, but the really interesting bit is we look at the write log waits, and we see there was over 82 seconds of time spent waiting on write log events when the transactions were fully durable, however less than half a second there. So briefly explain where these figures came from. We used the DMV's DMIO virtual file stats for the duration, for the number of writes and the bytes written, and also looked at the DMOS wait stats for the write log waits. So you can see quite a dramatic performance improvement there by delaying durability when we've got a workload of lots of small inserts. I'm quite surprised at how much performance improvements we got here. So then the second scenario we discussed was what would happen if we had the same amount of data, the same data in fact, but we were doing it in larger inserts. So this is simulating a different type of workload where we're inserting a large number of records at any one time. And you can see in the second two rows where fully durable, few large inserts, and delayed durability, few large inserts, there isn't really anything to be gained from delaying durability here. And this can be explained by looking at our 60K log buffer. My 25,000 rows presumably exceeded the 60K log buffer, and so our delayed durability wasn't really giving us any impact. There's nothing else really, it didn't really help, which had the side effect of not knowing whether all our transactions were written to disk in the event of a failure. So I think the conclusion we can take from these fairly simplistic tests was that if we have a workload where we're doing lots of small inserts, then there's something to be said for using delayed durability. However, if we have a workload where we're doing lots of large inserts, or fewer number of large inserts, particularly when we're exceeding our buffer size of 60K, then there isn't perhaps as much performance improvement to be got. Now, clearly these results were found on a simplistic test that I did. It would be necessary to test your own workload to see whether this has any benefit, and whether you also crucially consider whether you can tolerate any data loss. Considered also what would happen if we were using bulk inserts, perhaps more common in a BI data warehousing scenario. And here we don't expect to see much performance improvement because our bulk inserts will usually be minimally logged, and we're only logging page changes to our transaction log, so don't expect to see much performance improvement there. The Other new feature of SQL Server that might well help us here would be in-memory tables. Now, this hasn't necessarily been considered in these tests, so there's perhaps alternative performance gains to be had there. However, that will be covered in a later webinar presented by one of my colleagues. Okay, so in summary then, we have seen what delayed durability is, what the implications of using it are, potential data loss, and what scenarios and workloads it could potentially help us for to resolve transaction log write bottlenecks. And we see that lots of small inserts is a candidate for using this for performance improvements. Okay, and that concludes this webinar on delayed durability. I'll just see if there's anyone's asked any questions.